Hello and welcome to ATAR Notes 2024. Just so everyone knows, this right here is a pre-recording, but I will be in chat, me or someone else, there to answer any sort of questions that you might have. So at ATAR Notes, if you don't know, what we do is we concentrate on trying to get all of you the best possible ATAR in your final year of high school. So we have a fair amount of resources to do that. So we have study notes, which are quite useful to look up on. They're sort of like summarizations of all of the content that can be like very to the point, very useful in that regard in terms of time efficiency, I guess, if you're about to do an exam or something. We do lectures like the one here. We have discussions, videos, newsletters, and an ATAR calculator if you want to anxiously look at what you think you're going to get, and a bunch more other little things that we do. And we really should be able to give you everything that you could desire to be able to maximize your ATAR. So today we're going to be looking at Methods Unit 3, so some content from Methods Unit 3. It says down the bottom right, presented by Taja. That's not the case. My name is Vaughn Sampson. I'm taking over from Taja for this presentation because she was unfortunately unavailable. So today we're going to be looking at Maths Methods Unit 3 stuff mainly. So this is a lecture series. There'll be more lectures throughout the year that are in this series. Right now we're going to be covering Unit 3. So this is a little bit of stuff about Taja, not myself. I may as well introduce myself here. So I graduated in 2022 on the Gold Coast from the Southport School. I'm studying software engineering at the University of Queensland, so that's like programming, mainly some science engineering stuff in there as well. So if you have any questions about, my experience in grade 12, my experience in university, what you could look forward to, my specific course, then feel very free to ask that into chat. It'll probably be me there, especially towards the end of the lecture. Feel free to ask the more personal questions if you'd like to. So welcome to grade 12. We will help you ace your QCE, and that is hopefully the case. So as a little introduction, ATAR is the Australian Tertiary Admission Rank. So that means basically you're going to get ranked against everyone else doing ATAR, which I'm sure you've already heard a little bit about of during school. Today we're concentrating on the actual grades that get you ranked. So in year 11, you were really only ensuring that you would get your QCE points, you would pass everything, and then set yourself up for this year. This year you will be graded, and that those grades will go towards your ATAR. So you have 50% internal grades. That's your school has prepared certain resources that will grade you, and then external 50%. So you have one final exam, and that will be 50% of your grade. So it's pretty important this year that you concentrate on a more long-term sort of maintenance of knowledge, as opposed to some previous years where you could just be worried about the next exam. So today we're going to be looking at Unit 3, specifically integration, because lots of logarithmic stuff and differentiation has been covered before and already been covered. So we're going to be looking at integration, which I'm sure in school you would have just started, or you'll be going into more detail in the coming year. So some notes before we start. Please, it'd be good if you could try to have some material with you, so you could paper with you and pen, so you could try to work through the questions at the same time, so you could see where you've made mistakes and such. And it might be good for you to write notes as well if that's what you like to do. Now we're going to look at anti-differentiation. So we're going to look at definite and indefinite integrals. Those are two very important mathematical concepts that will help us. Well, definite integrals will help us look at the area underneath curves. So that's sort of a real application. And indefinite integrals are still important in understanding definite integrals and understanding some facets of calculus. Now, we're going to look at specific forms of integration, so that is exponential, logarithmic, and trigonometric. After we just look at the basic stuff where we're just looking at your more common rules when you're for example, integrating a polynomial. Then we have the practical application of looking underneath the curve, and the trapezoidal rule, which is sort of about looking underneath the curve. So in your syllabus, which is very good to look at, it's very good to look at starting the year and before exams, to look at the syllabus and break it down, because it'll give you an idea of what content in your head you should actually really concentrate on. When you're going to go over so many things in class, there's going to be so much in the Cambridge book, and a lot of it might not actually be useful towards your exams and your assessment. It might be more useful towards just a general understanding of the concepts. But this is the really important stuff, the stuff that is in your syllabus, the stuff that you will necessarily get graded on. So I would really recommend reading through all of your syllabus yourself and making notes. It's not fun, but I think it's like a 5 minute task that you can do that will definitely help you moving forward. So in this topic, students we're going to basically look at anti-differentiation, the notation, and how we actually work with the formulas. So there's different formulas that we expect working with exponential, logarithmic, and trigonometric functions. So then we're going to understand how to basically separate in integrals and definite integrals to be able to find useful things like the area underneath the curve. So then based on all that, we're going to get a general understanding of what is integration, how do we relate it to differentiation, and how do we actually get useful, applicable skills out of it. So we're going to look at as well the trapezoidal rule, and we're going to, looks like everything. Okay, so let's move on. Now this is a description, a sort of visual symbolization of what differentiation is. It's saying, okay, from the chicken, if you differentiate the chicken, there comes an egg, the change in chicken, and then if you anti-differentiate the egg, you should get back a chicken. Now that's not exactly the case, because in reality you would probably get something more like the chicken plus C, which we're going to look at soon, which is basically saying if you differentiate the chicken, and there's also a constant next to the chicken, it's an interesting metaphor, then when you differentiate that, this constant will disappear, which means that when you anti-differentiate, you have to add the constant again, but you don't know what it is, so you just put plus C, the common constant value. So we'll look at that soon. So the common notation for anti-differentiation is this symbol here. You have this symbol here. Then you have some sort of function. So that's function x here. And then you have dx on the end, which is saying the difference. So with this, you can often not actually have this dx in here, the difference in x. You can not have it in there. And with your working, you often won't write it every time. But if you were to write it in a proper way, it's good to have that dx in there generally. The notation for definite integration, which means basically you think about it like you're integrating between 2 points on a line, then it's very similar. So you have this same anti-differentiation, this integral symbolization, and then what you have is B and A. And that is A is the start point that you're looking at, and B is the end point. So what you're doing when you're doing definite integration is you're integrating between 2 points, and you'll understand what that actually means soon. What values does that give us? So what are indefinite and definite integrals? So the indefinite integral of fx is the function that gives us the original equation if fx is representing the gradient. So basically, if fx, let's say gx is equal to x squared, then if we were to differentiate that, so we had g differential of gx is equal to fx, let's say, so that's fx is the differential of gx, that would be equal to 2x, right? So then basically the integral of fx is then equal to gx. And that's sort of what it is. You're just reversing the process that you did. The only difference is it would actually be equal to gx plus c, because gx you could add plus 2 on the end, or plus any, well, or plus anything on the end, like you could add plus c on the end, as long as c is a constant value, then that value would have disappeared when you differentiated. So you have to add the plus c on the end again, and this time it could represent any value. And we'll look at that again in a second if that doesn't make any sense to you. So definite integrals, on the other hand, is not a function. We're not getting a function out of it. We're getting a number. We're getting a number that represents the area under the curve of fx from x equals a to x equals b. So let's say we have this line here, and this is a curve we have. Whoa, this is bugging out. Let's say this is a curve we have. Now, if we want to get the area underneath here, let's say we want to get the area underneath here, actually. Let's cut off and let's get the area in this spot here. Now, if this is A and this is B, and let's call this fx. There you go. Now, if this is A and this is B, this will get us the constant value that is the area underneath the curve between A and B. So there's a little description of why that occurs later. Bit hard to wrap your head around, and not necessary really to wrap your head around in reality. But if you're an enjoyer of mathematical theory, maybe you want to look into it, why that actually is the case. But what you need to know to pass these tests and pass your assignments is to understand what you can actually do with it, as opposed to why it is how it is. So we're going to look at derivatives. So, to understand antiderivatives. So if we derive x squared, that will result in 2x. If we derive x squared plus c, that will also result in 2x, because we're assuming here c is a constant value, it's not a variable. So c is any constant value, that will become 2x. And you can see that here, there's that extra 1, and that disappears. Here is pi, that disappears. Now, just a little recap, if we were to derive, let's say 2x cubed, that would become 3 times 2x squared. So basically, you really should be pretty comfortable with these general rules to quickly derive things, because they're very useful, and they will also be useful in anti-differentiating and understanding. Basically, you'll get a result when you do anti-differentiation, and then you're going to look at the result and be able to consider, is this result correct? So if you understand these general rules that we have to go through, I think some rules are on your formula sheet, then you will be able to apply those. So, yep. So what is the antiderivative of 2x? Well, we know that x squared plus 1, x squared plus pi, x squared plus anything always results in a derivative of 2x. It doesn't matter what this constant value is on the end, it's 2x. So if we antiderive 2x, if we do the anti-differentiate, 2x, we have to get this plus c, because this plus c represents the possibility of it being pi, of it being 1, of it being 0. It represents the possibility of there's any possible constant value, and that's the case. So, yep. So this is sort of a general rule for finding the anti-differentiation. If all you had was if you were finding the anti-differentiation of x to the power of n, to the power of anything, and if that's all that was in there, you can utilize this formula here, and we'll prove that in a second. So let's say we just have xn, that would be equal to 1 over n plus 1, given this formula, xn plus 1 plus c. So in that scenario, we could then prove this by then deriving this. So let's get the, let's say this equals fx. Now let's get the differentiation of fx. So that would be equal to, so we have this constant value at the front still, because n is a constant value as well. Now we multiply that by our answer. So our answer will be in brackets n minus 1, because let's say it's x3. If we derive that, it would become x2 times 3. So we have times n minus 1. That's this value up here is now thrown out the front. And then times x n plus 1 minus 1. So the power goes down when we derive. Plus c? Nope. We don't have the plus c because it's just a constant value. So if it's a constant value that's sitting there on its own, we get rid of it because the power keeps moving down, and that's sort of a constant value outside of x to the power of 0. So c can always be considered. You can consider it like c times x to the power of 0. So then if anything's to the power of 0, then the next step is we remove it. So if that confuses you, just ignore it. Just think a constant value disappears when we derive. So then we can expand this. We have, this should be n plus 1. We have n plus 1 over n plus 1 times x, n equals xn. So that's just a little proof of, okay, this rule leads to this, and if we derive this, it leads back to our initial value that we initially integrated, just to prove that this is true, that the differential, the anti-differentiation of xn is equal to 1 over n plus 1 multiplied by x to the power of n plus 1 plus c. So let's actually work with this as an example. We want to find y. So when we want to find y, it's sort of like saying we want to find fx, because usually when you say fx equals etc., you would have it so y is equal to etc., y is equal to fx. So this is our derivative. That's what it's saying here. Our derivative of an initial value is this. So now we want to get the anti-differentiated value of this. If we follow this formula, that would be equal to 1 over, so n here is 1, because this is to the power of 1, so 1 plus 1, multiplied by x, 1 plus 1, multiplied by, we have this constant value at the front, 3. Now we do have a plus c, but we also have this 2 here. Now this 2 also is its own term. So we also have to sort of anti-differentiate it separately. So we also have a plus 2, or sorry, a plus 1 over 2. Am I making a mistake? Plus 1 over 1 times x, 0 plus 1. So this culminates in 1 over 2 x squared times 3 plus this should have a 2 at the front, plus 2x plus c equals 3 over 2 x squared plus 2x plus c. Now it's my opinion that, and it's up to you what you choose to do, but it's my opinion that applying this formula up here leads to very large expressions like this, which I would say to me is undesirable. I think it's better if you sort of get used to being able to just look at it and feel it out. So you know, okay, so there's one of the terms in here is 3x. So okay, what could be derived to make 3x? That would be my question. I know that there must be an x squared, factually, based on the fact that if x squared is derived, it becomes x, and that's the only thing that will become x if it's derived. So I know there must be an x squared. Now, if we did derive x squared, it would become 2x, but we want 3x instead. So we're probably going to have to put a 3 over 2 out the front here, so that it becomes 2x times 3 over 2, which is equal to 3x. So this is sort of useful to get used to these patterns. If you can't, I know some students, it's just not really their way of learning, getting used to just like intuiting how to turn 3x, like what creates 3x, sorry, if you derive. So this is a useful formula if you're one of those students that likes to basically rely on formulas to an extent, which is more reliable. And so I definitely think it's sort of up to you what you prefer. Now, one note is something that might help you a little bit is that if we have the differential of 3x plus 2, it is the same as the differential of the anti-differentiation, keep making that mistake, the anti-differentiation of 3x plus the anti-differentiation of 2. So that might make this formula a little bit easier since they're the same. So you basically apply this formula twice, as I did down here. You apply this formula twice because you are anti-differentiating both of these terms separately. And then each one of them would have their own c, I guess, but that just culminates in one c because c is any constant value. So any two c's lead to one constant value because they can add together. So yep, over here they used that strategy. They split it into two to make it more obvious that you can utilize this formula here. So let's find the indefinite integral. So that's the typical anti-differentiation of 4x to the power of 5. Now, my instinct, again, is not to use that formula. It's just to think, okay, it must have been x to the power of 6, which means if you derive x to the power of 6, it would become 6x to the power of 5. So then there must be it must be 4 over 6 x to the power of 6. And the reason is because if we derive this, we will see, okay, there is a 6 multiplied by our 4 over 6 multiplied by our x over 5, which equals to 4, not x over 5, sorry, x to the power of 5, which equals to our 4x to the power of 5. So that would be my instinct, and I know a lot of students do it like that. They just sort of look at it and they can feel out what must create it. They're sort of doing, they're sort of reversing the process a little bit. They're finding out how to create this value here as opposed to applying any formula. What would you derive to create this? Therefore, what does this anti derive to? On the other hand, let's also utilize the formula to do it because that is a more consistent, reliable way. So we have 1 over n in this scenario is 5, so 5 plus 1 multiplied by x to the power of 5 plus 1 multiplied by, plus c. So in this scenario, we have, we actually have to multiply this by 4 as well. I do make that mistake a little bit. One thing that's actually very important to note that could help you just understanding this is, since constant values basically are kept out the front during anti-differentiation and differentiation, this here is equal to this. So we can, if we're able, we can remove a common constant value outside of the equation, which can make it easier for us to look at. So it's easier to apply this formula here. So if there's a 3 here, you can just move 3 outside, and that makes our goal a little bit easier. So yep, we don't want to forget this 4. We have this constant value 4, and then we multiply it by our formula here, and that is equal to 4 over 6 x to the power of 6 plus c. And if we move 4 outside, we could have it like in brackets as well, everything in brackets. So the 4 gets multiplied by everything, but again, we don't write 4c because c just represents any possible value. So 4 times any value includes any value, so we can just keep it at c. So let's utilize the formula for 7x to the power of 13. Is equal to 7, so we have our constant value that we shouldn't forget, multiplied by 1 over 13 plus 1 multiplied by x 13 plus 1. Always remember to add that c on the end. So that is 7 over 14. Now this is actually a mistake up here. I've forgotten to simplify it a little bit. Fractions, you should always try to simplify it, and we have to do the same over here as well. Multiplied by x 14 plus c. So that's equal to 1 over 2 x to the power of 14 plus c. So we'll rub all this out just to give us some space for the following questions. So this one's a little bit harder because we're not looking at numbers, we're looking at representations of numbers. So we assume a and b in this scenario. We're going to assume that they're some constant value. So we're differentiating a multiplied by x squared plus b multiplied by x. Now the first thing that's good to do if we're going to utilize this formula is we separate these terms into their own anti-differentiation sort of sets. So we have bx. Now another thing we can do is we know that we're assuming a and b are just these constant values because that's the type of question you get in Unit 3. So we are going to move a out the front to simplify everything for us, and we're going to move b out the front for both of these integrations. So now what we can do is we can utilize this formula for each of them. So for the one with a out the front, we have 1 over 2 plus 1 multiplied by x 2 plus 1 multiplied by a. And then we have to add our second term here. So that is 1 over 1 over 1 plus 1 multiplied by x, 1 plus 1 as the power there, and then all multiplied by b. So that should be equal to a on 3 times x on 3 plus b on 2 times x to the power of 2. Okay. So lastly, we have this one here. Now we'll try to apply this formula. Just consider that 1 over x to the power of 2 is the same as x to the power of minus 2. So let's do this. We're going to integrate 1 over x to the power of 2. Now that's equal to x to the power of the integral of x to the power of negative 2. So from here we can apply this formula all the same. And this formula might even be a little more useful when you're working with like you have a negative power, because it's just a little harder to look at. So this is equal to 1 over minus 2 plus 1 multiplied by x minus 2 plus 1 plus c is equal to minus 1 I'm going to do times x minus 1 there plus c. So that is minus x to the power of minus 1 plus c. And hopefully that is all correct. I could have made a mistake, as you do, but I think generally that's the idea that we're going with here. Some of these you can look at them and you can see sort of patterns that you would expect. For example, I can see that, okay, the power here will become to the power of 14, and then to get the 7 out the front, that must necessarily mean that I have a 7 over 14 at the front. So those are some patterns that we have. That you can use instead of using this formula when you get this specific formula here, when you get really comfortable with these basic integrals, especially when you're moving between differentiating and anti-differentiating so often, you will start to see just the general patterns there. Now, this is very important. Don't forget to add the plus C. I know that's a big problem that I had during my time in grade 12. I would very consistently forget to add that plus C, which is extremely important, obviously. Otherwise, you're missing a value, especially when you start doing multiple layers of integrating, because what you can do is you can have to do the integration, sorry, of the integration. And like, let's say we had the integration of x, it would become, okay, now we want to do one level of that. So we have 1 over 2 x squared plus c, and now we integrate this as well. So then we have 1 over 6x to the power of 3 plus cx plus d, and d would be another constant value. So that's sort of what we're looking at here. That's why C is very important, because especially for multi-stage questions, because it remains consistently relevant when you have to do multiple levels of integration, which is actually quite useful for some real life applications, such as like, for example, if you're able to make a line that represents the displacement of an object in physics, then if you differentiate that, you will get a line that represents the velocity of the object at any point. And then if you get the differential of that, it'll become the acceleration of the object. So there's many layers of differentiating to get real life applicable values. And then let's say you had the the acceleration, and you wanted to find the possible displacement. Then you would have to do 2 layers of getting an indefinite integral. So C is very important to keep. Otherwise, whatever you've written is not mathematically valid. So now we have definite integrals. So they give an actual number. They don't give a formula like an expression like we were getting here. So when we differentiated this, it wasn't a constant value. It's an expression. It's a function. Now we're going to get an actual number here because we're going to use these 2 numbers to evaluate something out of the function that we get. So I'll go straight into doing an example here. Here we're going to derive between these 2 points. We're going to get a definite integral between these 2 points of x minus 4. So first I'm just gonna derive x minus 4 just to conceptualize this. So that will result in 1 over 2x squared minus 4x plus c. And we can see if we did derive, that would become this, and then the plus c would become sort of plus 0 on the end. It would become nothing. So that makes sense. Now, when we do the definite integral, this is equal to this. So we have our 1 over 2x squared minus 4x plus c. And we put these in these square brackets, and then we put our same numbers that we have here at the end of these square brackets, because we still haven't used them yet. Now what we do is we substitute the first number in. So we go 1 over 2, the top number here, so that's 4 in this scenario, times 4 squared, minus 4 times 4, plus c. And then we do a negative, big brackets, and substitute the second number in. So 1 over 2 times 0, that's our second number, minus 4 times 0, plus c. So that's equal to 1 over 2 times 16 minus 16 plus c minus c. Now, whenever you're doing this definite integral, what you'll realize is if you start always doing plus c, if you start using the plus c, you realize that the plus c cancels out every single time. So with definite integrals, you don't actually even write the plus c, because it's just mathematical knowledge that no matter what, that plus c will cancel out, because you substitute the top number in, and then you subtract everything where you substituted the bottom number in. Which means, since c has nothing substituted into it, it'll always be c minus c. the top number being substituted in will always have a c on the end, and the bottom number being substituted in will always have a minus c there. So we could even go through and we could just remove all instances of c existing in here. So this is what we end up with. We end up with 8 minus 16 is equal to minus 8. So that's our result. That's our definite integral. Now, the fundamental theorem, let fx be a function continuous in the closed interval, a is smaller or equal to x is smaller or equal to b, and let fx be a primitive of fx. So we're saying fx is the indefinite integral. So what we're doing is we're getting the indefinite integral and we're substituting in b, and then we're subtracting our substitution of a into the indefinite integral. So we can go back and sort of apply it in that way as well. We'll go back here and we'll redo some of this question by applying that sort of form instead of using these square brackets, which I think are more commonly used. So now we have, let's go all the way back here. Okay. So we will set this equal to fx, as is described over here. Now we'll say, okay, therefore fx is equal to 1 over 2x squared minus 4x plus c. So now we have this over here with these definite values. This definite integral has f4 minus f0. So that becomes 1 over 2, 4 squared minus 4 times 4 plus c minus 1 over 2 x squared times 0 minus 4. That's my mistake. Go back here. That cannot be rubbed out. Okay, 1 over 2, 0 squared minus 4 times 0 plus c. And that should be all a minus out the front. And that should be a plus. Okay. So basically, that results in the same thing that we found before. So the square brackets are sort of a notation that I think is most widely used when you're just solving by hand, because it's just quite efficient. And you don't usually put the plus c in there. So definite integrals, you get the basic integral and then you substitute b into it, and then you subtract the integral with a substituted into it, and that's your answer. You could ignore c, given that c will always cancel in that equation. Is that the same one we did? Yes, it is. Yep, so this is sort of the basic notation that we tend to like to use. And then we separate it into these separate sets of brackets. So yeah, do remember it's very useful that you can divide the integral up. When two things are added together, you can divide it into separate integrals, and then you can evaluate from there, which can make, integrating a lot easier, especially when it gets like complicated like this, all the way down here. If you can separate those, it will make your life a lot easier. So evaluate the following definite integrals. So we have our range here. We have from 1 to 4, 2x. So I might want to go back and represent something here now that I think about it. I think I've already been over this, but we should sort of take a little look at what this actually looks like. So what we're finding is we're actually finding the area beneath the curve. So if we put lines here and we said this is A and this is B, and then if this was fx, then we would be finding this area in here. And that's sort of what this is actually useful for in when we're applying it. So let's do that. Let's find the area under the curve 2x between the points 1 and 4. So this line would look something like this, and then we have this point 1 and this point 4, and this is going to find the constant value, that is the area in between those 2 points under the line. So this is equal to, now we're going to put the integral without c in these brackets, these square brackets. And then we can evaluate those. So that is equal to 4 squared minus 1 squared. So again, I'm substituting 4 in, then I'm putting a minus there and substituting the 1 into that second instance. So that's 16 minus 1 is equal to 15 is our answer there. So that's the area in here on this line there. So now we're going to look at a much larger line. So this line might look something like, this. And now we're going to find the area between 1 and 2. So that would be, we would have a 10 times, we'd have some fraction at the front probably, multiplied by x to the power of 5. Now we know it creates 10 at the end, so there would probably be a 2 out the front here. So 2 times 5 equals 10. So if we differentiated this, it would equal this here. Then we have our range, our domain, 1 to 2 is equal to, we have 2 times 2 to the power of 5 minus 2 times 1 to the power of 5. So that's equal to 2 times 2 to the power, that's equal to 2 times 32, I believe, minus 2 is equal to 62 all up. Now lastly, here we have a much more complicated one that we could decide to, I'll rub some things out so we have the space to split this one up into multiple different parts. So first I'll just do the basic integral. Now you don't have to separate it into multiple separate parts if you find that too laborsome, but you can. So then the answer to this would be and now if we were to apply it to the, let's put a little, if we were to apply it into these brackets here, these square brackets, we would get rid of the c because that value we know is going to be cancelled out, so we don't generally write it into the brackets. good to put brackets around the second part because it's very easy to start writing, and I've done this before, talking from experience. It's very easy to put this minus here and then start writing the second, the negative part of the integral, and then you make the mistake of not putting brackets down and just writing the first term, and only the first term actually becomes negative. So you will end up with an incorrect result. So it's good to put brackets outside, or if you're very good at doing this, you can just swap the sign of each term as you go. So yeah, some of these questions can be quite long and more laborious, but really a lot of these sorts of questions are just, I feel like they're put in exams just to allow you space to make mistakes, really, because that's a lot of what these exams are about, I guess, just seeing how often you'll make mistakes. So I'm going to expand the brackets here. So that becomes a plus. This becomes a negative. We'll just put that to, it'll become a plus actually, because there's a plus, but it gets multiplied by -3. So there's a lot of addition of fractions there, which there's no point in us spending too much time on. Obviously, if you had a calculator, that wouldn't be a problem at all, but otherwise you probably could just manually go through all of this and add these fractions, considering they're all only 3 and 2 as the denominator. So basically what we're looking at here is, again, final little recap on the idea, because I think some people have never actually seen it before at this point. Basically, we derive what's in here. We derive the function. Then we substitute in the first value as all the x's in the function, and then we subtract the function where -3 or the second value is substituted in. Saying first value and second value might not be the best idea because some people consider this the first value and this one the second value. That's why you'll see often A and B. And the reason that actually is because usually when you're looking at the area on a line, the A will come first, the B will come there. So I'd say maybe A is actually the first value. So maybe it's better to say substitute in the top value and you subtract the bottom value. Substitute it in. So let's look at sort of more complicated forms of differentiation. Now, when we derive e to the power of x, we know that we get e to the power of x. Now, that's just a special. That's basically what makes e a special value. It has this special place in calculus. It's this special value that has that function. Where e to the power of x derived equals e to the power of x. Now, that doesn't mean e to the power of, let's say, ax plus 1 is equal to derived, sorry. So let's derive, let's say fx equals this. Now, the derived version of fx does not equal to ax plus 1. It does equal to basically the differential of what's up here multiplied by this. So let's say we have, and I'm just doing a quick, I think you've probably all seen this before, but if we have fx equals to ex squared, then the differential is equal to 2x times ex squared. So that's the differential of what's up here getting multiplied down to there. And that's our system. Should be equals. So that's a pretty simple system of deriving. There's a pretty simple formula that you use a process for this specific type of value, which is e, this magical value that exists in calculus. Now, how do you integrate? Well, integration is pretty similar. So if you integrate e to the power of x, then you will just get e to the power of x plus c. And that's because if you derive e to the power of x, it'll be the derivative of x, which is just 1, multiplied by e to the power of x. So it'll be e to the power of x. On the other hand, you often will have much more complicated situations. So this is the best general formula to look down at to look at here, because it covers everything. These only encompass certain forms. For example, this only encompasses the form where what's up here is a linear function. This covers any type of function. So if you ever see the differential of a function multiplied by e, which has the function as its power, that means if you derive this, it'll just be equal to e with the function to its power, and then of course plus c, as typical. And that can obviously be applied here to this linear one, because we have, in this scenario, let's say we had a e to the power of ax plus b. Then if we derive that, it would be equal to e to the power of ax plus b plus c at the very end. And that's because we're in this form here. This derived only has a, so a goes out the front when we derive it. So then when we antiderive it, we would get rid of the a. We'd do the inverse process. In this scenario, we don't have the a out the front, so instead we have the 1 over a there, because we assumed that when we derived, if we did derive this, the a would go out the front, and then it would be a over a, and it would all cancel. So basically, understanding these formulas, understanding why they are sort of how they are, is I think the best way to do it, because there's lots of different formulas, but if you understand the basic logic, and the easiest to look at is this formula here for that, then this encompasses all of those different forms. And even if these other forms, if knowing them does allow you to do your working a lot quicker, and they are very useful, understanding the most basic formula is definitely the most versatile. Understanding these ones is more so useful for doing work quickly in an exam, basically. So now we're going to look at logarithmic integration without actually doing any examples here, which maybe at the end, if we do have some time, we can go back and create and generate some examples for this. So if we can recall from Unit 3, we can differentiate log x. The differentiation of log x creates 1 over x. Now I'm hoping you've seen that currently. I'm hoping you've gotten that far in Unit 3, because I do think most schools, you start year 12 the year before a little bit. You do a little bit of content the year before. So yeah, if we derive, usually you'd say ln x is usually what they use. If you derive ln x, you get 1 over x. If you derive ln fx, you get the differential of fx over fx. And that's also down here. So then you can do the opposite by deriving. Now this should probably have a plus c here. They've forgotten the plus c in these examples. You can never really forget the plus c. So these are our general formulas, similar to our last page. These are just our general formulas that if you understand them, you will benefit. Now this is the similar example of we have a linear function inside of the log, and then it will end up looking like this. Looks very, very similar to how this is generated, because it is very similar. The most general use formula, though, the one that aids us the most, the one that we can basically take anywhere we want, the one that encapsulates this one here and this one here, is this bottom one. So the integral of the differentiation of fx over fx is log fx, or ln fx is usually what we use, plus c. So if you can remember this one, this will encapsulate everything, and that's the best one to remember. So let's do an example. Okay. So we're going to do the definite integral of 1 over x, sorry. So now we can apply our knowledge of our formula. We know that if we did derive ln x, it would be equal to 1 over x. So that means in these square brackets, we're going to have necessarily lx there. We have e to the power of x, or e to the power of 2. I don't know why I wrote x. That would be a very hard thing to solve. And then we have e down the bottom as well. Okay. So this becomes ln e squared minus ln e. That becomes 2 ln e minus ln e, which becomes 2 minus 1, which equals to 1. And that's just using our logarithmic rules. If we have a log base b and then it has b inside of it, that is equal to 1. And ln is equal to log base e. So we have ln with an e inside of it, that is equal to 1. So now there's a more complicated one. This looks like a linear function is inside of our log here. So we're going to do a definite integral over this here. Now we could just check a log. We could say, okay, what if we derived ln 2x plus 1? What does that create? If we derived this, that would derive down to, might want to put it in a place where we have a lot more space. If we did have ln 2x plus 1, that would derive down to 2 times 1 over 2x plus 1. Because remember, the differential of what's in here goes on the top. And then what's in here also goes on the bottom. So that means at that point that we look very similar to this. The only difference with this is there should be a 2 on the top, and that's sort of what we're missing on this side here. So we could assume, okay, so we must have a constant value of 1 over 2 getting multiplied by this, 2x plus 1. So we can take our 1 over 2 out the front. Oopsie. 2x plus 1. And now we're looking like we're in the right form. So we can utilize this logarithm that we hypothesized would be related. And we can't forget our 1/2 as well. 1 to 0. So that means we have 1 over 2 ln 2 plus 1 minus 1 over 2 ln 1, because our 2x becomes 0. So we could just put 1 over 2 outside at the front of everything, and we say ln 3 minus ln 1 is equal to 1 over 2 ln 3 over 1, which is equal to 1 over 2 ln 3, if I haven't made any mistakes. Yep, okay. And this over here is just using our logarithmic rules. I know that if ln whatever subtracts ln whatever, then that is equal to ln, let's say ln a subtracts ln b, that is equal to ln a over b. And that's just one of our rules that you should probably get comfortable with if you don't know it already. Okay, so we have another example here. We're going to, okay, yep. We're going to find what is fx if we know that the differential is equal to this. So let's utilize that. We're not doing a definite integral, we're doing an indefinite integral, but we know this point here, so we can actually find what c is utilizing this point. Find that c is one true value, instead of it just representing a whole bunch of possible values and an infinite amount of possible functions. there's only one function for which this is true and for which f1 is equal to 0, because we're going to have one c value. Okay, so let's prove this. Let's utilize this. So we're going to get the indefinite integral of 3 over 4x minus 1. Now, if I were to look at what would the let's say fx did equal ln 4x minus 1, then the differential of fx would actually have to equal 4 over 4x minus 1, and instead we have 3 over 4x minus 1. So I'm going to assume that there was actually a multiplies a coefficient of 3 over 4 there, so that 3 ends out on top. So if I were to derive this, you would see why this would make sense. Equals 4 over 4x minus 1 multiplied by 3 over 4, which is equal to 3 over 4x minus 1. If you find sort of this difficult just to look at it and then interpret what coefficient was there, then do just memorize and utilize these formulas. It's sort of just a personal way that you can choose to do it. Do you want to basically just memorize the formula, memorize how I turn this into that, or do you want to have sort of a different type of intuitive understanding as to how you can basically reverse engineer what you're looking for? So I know that this is equal to ln, or we'll put the coefficient out the front, 3 over 4 ln 4x minus 1 plus c. Now, so we've basically found what it's equal to, but we just don't know what this plus c is equal to, unless we choose to substitute in values, because we can substitute a value in. We have, when we substitute 1 into all values of x, oops, that's a little mistake there. When we substitute 1 into all values of x, then we know that the result is 0. So we can say 0 is equal to 3 over 4 ln minus 1 plus c. Now, that's a terrible mistake. I was very confused for a second. 4 times 1 minus 1 plus c. Sorry about that. So now it's 0 equals 3 over 4 ln 3 plus c. So now c is equal to minus 3 over 4 ln 3. So that means we can substitute that into our function, and then we have our final function. So we can say y, or in this scenario, it's probably better to write fx, because that's what it's asking for. It wants you to find fx. Fx is equal to 3 over 4 ln 4x minus 1 plus or minus 3 over 4 ln 3. They both have a coefficient of 3 over 4, so I can do my logarithmic subtraction. So that becomes 3 over 4 ln 4x minus 1 over 3. And that's probably should be our final answer, unless I made some little error. They don't actually bother even trying to solve it any further. I think the last step would be to create a 3 over 4 ln and then use your logarithmic subtraction to figure out what the answer is there. So basically, to summarize this sort of problem, what this is telling you to find an indefinite integral, and then to be able to substitute one value in to find what is the line that fits with that. So we found the indefinite integral, which has the plus c on it. So that's not a specific function. That's just a bunch of different functions, because there's any possible value of c. If c was 1, if c was pi, if c was 1 million, it would create a different function. But by substituting in the values, since there's only one c, we can find that there's one possible value of c for which f1 is equal to 0. So we were able to do that, and that allowed us to find an actual single fx that exists for which this is the integral, for which this is the differentiated value and for which the line goes over this point. So we can look at trigonometric integration. I'm just going to take a quick look at the amount of slides we have left. Okay. So trigonometric integration, we basically, by understanding your trigonometric differentiation, you're definitely going to be benefited. The most common ones that you'll look forward to is the differentiation of cos x is negative sine x, and the differentiation of sine x is just cos x. So I think these rules that you can see right here might be in your formula sheet. Now these are just obviously the reversing of that process there. So we have sine x is equal to negative cos x, which is also, so if we differentiated negative sine x, we would say that is equal to cos x. And then remember, you always have to add your c. If we differentiated negative cos x, on the other hand, that would just be equal to negative sine x plus c. Because if we differentiate this, it becomes that. So look at these formulas. These are sort of, I think, the ones you get in your formula sheet, which aren't exceptionally helpful, considering there's just much more, like this sign, and it only has an x inside of it. But for example, if you can derive, let's say we have cos 2x plus 1. If we derive that down, that would be negative 2 sine 2x plus 1. So that means, based on this being a very consistent process, we can also derive, let's say we had to derive negative 4 cos 4x, we would then find out that that is equal to negative sine 4x. So this is like a general, this is a situation with these trigonometric integration formulas that I would say just practicing and getting a more of a general understanding of like how these work. Like if you understood exactly like what I did here, you're probably completely fine. If you don't understand what I did here, then just practice. Just practice doing these questions. The best way I think to understand a lot of these questions, to get an intuitive like understanding on how to complete these like very simple, familiar, just integrate this questions, is to basically understand how to differentiate. And then if we can differentiate, we can probably reverse differentiate. We can anti-differentiate. So this is a more generalized formula here that is able to utilize using a linear function inside. But I think generally the formula would sort of look like, if we expect the differential of fx multiplied by sine with fx inside of it, that would be equal to minus cos fx. And that's our general understanding. And similarly, if we were looking at the differential of fx multiplied by cos fx, if we were getting the integral of that, we would see it would become sine, no negative here, fx. So that's our more generalized formula where we use fx. I don't know why I don't think they give it to you in the formula sheet. I don't know why. But it's sort of, to be honest, very similar to like when you have fx. When you derive that, you get the differential of fx out the front. And then you get fx. Cos and sine are a bit different. If you derive cos fx, you get you get the differential of fx out the front multiplied by negative sine fx. So it's very similar to this process here. These two processes are very similar. The only difference is cos becomes minus sine and sine becomes cos. And that's sort of the difference. But we do move this body that we have here inside cos out the front after differentiating it. So let's actually sort of apply that. We want to find the definite integral of some of these trigonometric functions. So let's start with the first one. So in this scenario, it's good to, like, even if you sort of have an understanding, it's good to look at the formula sheet, because you can immediately just apply a formula without having to worry about making any possible mistakes or misremembering something. So the formula sheet states that this would become negative cos x plus c. So we can just say, okay, this is negative cos x plus c. And we can ignore the c because we're doing definite integration. Our 0 and our pi on 4 out the front. So then we can just substitute in values. So we can say this is equal to negative cos pi on 4 minus, because remember we always put a minus brackets out the front when we're substituting in the 0, cos 0. So that would be equal to negative cos over 4. We could be able to use our sort of magic triangles if we wanted to. I believe that would be equal to something like this. Minus, which means plus 1. So we have 1 plus this here, unless I'm misremembering. I haven't done trigonometry in a while. So that should be our value there. Now, with this one, we can just apply our formula. With sec, I think generally you're just going to apply a formula. They don't give you extra complicated ones. Generally, yeah, with sec, you're definitely going to apply a formula, I'd say. At least my experience last year doing exams, or the year before last year. So let's apply this formula. So this would be equal to, we have a definite integral, so we want to use those square brackets. Now we have it's playing up. We have tan x plus c, I think it was. Yep. And then we substitute in pi over 3 and 0. So that is equal to tan pi on 3. And we can, remember, you can add the c in. I don't think you get punished for it, but you don't need to add the c. And that's just a habit I have doing myself. Sometimes I can't rub it out, though. Whoa. Okay. We've lost something. Okay. Tan x. This is playing up a little bit. I want to try to rub everything out. Okay, that's a bit better. Whoa. Give me a second. It's just PowerPoint is not giving me a very good time. Okay. It's a problem with my computer probably. Okay, so that's equal to tan, and we're following the formula sheet here. Tan x, then we have the definite integral, so we have these two boundaries. So then we have tan pi on 3 minus tan 0, which is equal to tan pi on 3, which I'm not going to bother apply the magic triangles immediately right now, because I don't think we have enough time to go deep into trigonometry. But at that point, you would apply your triangles to be able to find what sine pi on 3 over cos pi on 3 is equal to, if you wanted to simplify it down to get rid of sine and cos there. Which generally, like in an exam, you'd probably want to do if you're doing the definite integral, when they sort of want a very simple number for the area, generally. So this is the definite integral of 2 cos and then in brackets 2x there. Now that's equal to negative sine 2x. And you can, you can postulate that, and then you can actually be able to check that by then differentiating this and making sure it equals the same thing when you go back to there. I'm having immense trouble with the pen behavior on this slide. So that would be minus sine 2x pi on 4, 0. Minus sine 0. We can't forget that. And our answer is negative sine pi on 2, which is equal to 0, I believe. Or it's equal to negative 1, sorry. So now we're going to look at actual applications of doing our definite integration. So I'll quickly look at how many slides we have left, because we have a fair amount of time left. Okay, so yeah, we have a fair amount of slides left as well. So if we do finish a little bit early, I'll probably just go back and do some examples of integrating exponentials, because we sort of skipped over that. So let's go back to where we're supposed to be. Applications. So the function of integration was not invented to do backwards differentiation. It had a different purpose. We benefit from doing definite integration to find the area underneath curves, and we can also find volumes of certain objects by doing that. Like, for example, in specialist maths, you would probably end up dealing with finding the area underneath a curve and then extrapolating that if that curve was a 3D, like cylindrical styled object, by rotating that curve around and finding an area based on using some formulas. So there are real life applications in finding areas. I'm sure engineers use it a lot in finding, let's say, like how much concrete they need to fill a certain shape when they're constructing a building. So the function of integration was not invented to do backwards differentiation at a different purpose, to find the areas under curves. And remember the area of a circle, pi r squared, and the volume of spheres is that. So this is talking about how basically we can utilize this formula to actually be able to find, if we look at a circle, we can utilize an understanding of a circle to actually be able to find the area, the volume of a sphere with anti-differentiation, which I haven't actually done myself. That's probably something that I'm sure Taja wanted to quickly show you, but I'm not gonna bother waste any time trying to figure that out right now. So let f(x) be a function continuous in the closed interval a is smaller than x is smaller than b, and let f(x) be a primitive of x. Then we've already been over this. So this is a repeat of the slide of the idea that we can use our basic integral idea to be able to find our definite integrals. We get our basic integral function, and then we substitute b into it, and then we subtract a substitution of a into it, and that gets us our area underneath the curve. So let's say we had a line like this, and we said the line is y is equal to 2 over 3 x. If we wanted to find the area between 1 and 4 under the line, so that's this area I'm coloring in here, that means we would use a differentiation of 2 over 3x between the point 1 and 4. And we could follow this function here. It would become like this. We would have 1 over 3 x squared, 4 and 1 is equal to 1 over 3 times 16 minus 1 over 3 times 1 is equal to 16 over 3 minus 1 over 3 is equal to 15 over 3 is equal to 5. So this is our general idea, and this can lead to actually quite an array of complex questions. So the reason behind the theorem. Now this is not especially easy for everyone to wrap their head around, and luckily it's not incredibly important, because in this maths course that you're doing in high school, you're not worried about writing an explanation of maths theory generally. You're going to be worried about actually applying just like the basic formulas and skills to be able to understand things. You're not a theorist, but in theory, you can imagine the blue part of this sort of area, this area here. Let me find it. You can imagine the blue area under this curve here was divided into infinitely small subintervals with a width of the difference of x. So that is our difference of x that we think about in differentiation. Now, each slice being so thin and multiplied by the height of the actual rectangle here. So this would be like all these slices sort of looking like this, infinitely thin and multiplied by the height. If you were able to get the sum of all of those together between A and B, then you would correctly get the area underneath the curve. And that's sort of what this integration is actually doing functionally. So if you want to get your head around that, and it's quite hard to wrap your head around it, it might just be good to look it up and read a little bit about it, because if you're a math nerd, maybe it'll increase sort of your interest and understanding of the concepts here. Other than that, if you just want to apply it, that's what we're going to get into now. So this is an example here. We want to find the area underneath the curve. Let's say we have this curve. So this curve is just x. So y is equal to x will look just like this. Now we want to find the area underneath the curve between -2, let's say -2 is here, and -1. Now you might think, okay, there's a problem here. There's not actually an area underneath the curve. Well, instead we're going to get a negative area underneath the curve, because we are under the curve. So we're going to get this area in here, which is a negative area, because we are underneath the curve. So you might have a problem thinking, okay, but the area should be positive. Instead, what you consider is that you should just convert it to a net signed area. So what you're trying to find is the area between the curve and the line often. Depending on the question, what you would usually do is you would hand in a net signed area. So the area between the line and the curve is what that would be called. So this would come out as negative, as it does here. Yep, it does here. You would just say, okay, the area between the line and the curve is 3/2 units. You get the net signed area. Now this complicates things a little bit more later, or this allows some more complicated ways that we're going to deal with lines, because you might have a line that sort of looks like this. And at that point, it has these different sets of areas underneath the curve when it hits the curve, and then you have to interpret that a bit differently. So, and this is showing how you can do that. So if you have these two areas here, and you arbitrarily split them up, now you can get the area of each one separately. So that is A to C, whatever, plus C to B, and whatever's in there. And that will be the same as actually getting A all the way to B. So what you can do with these more complicated lines that dip above and below the curve is we can get A to this spot here. Let's call this C. And then C to this spot here. Let's call this D. And then D to B. And that can be our separate sets of areas that we can evaluate separately, and then we can get the sum of those areas, and that would get us the areas, the shaded region between the curve and the x-axis. Otherwise, what would happen is these areas would end up being positive, these areas would be positive and these would be negative. And when we sum them together, when they're automatically summed together by evaluating this, the negatives and the positives would cancel out. Instead, we prefer to find each of these separately, putting absolute brackets on the outside of it, the absolute value brackets on the outside, which means even if it's a negative number, we just flip that. If it's a negative number, we flip that to positive. If it's a positive, it stays positive. So if we evaluate these separately, we can turn all the negatives into positives, and that allows us to get the actual area underneath the curve. So here's an example of them actually solving an area. So this is the equation of the curve. So if this was graphed, you would see a little x to the power of 3 minus 4x, and that's our line. Now we want to find the area between minus 2 and 2, and then they do it, and then you realize, oh, okay, our result is 0, which is definitely a problem. So that's why then you can separate, and that's because this area is the same as this area, except this area is negative. So then when you add them together, it's 0. If you just find one of these areas, you could double it, and that'll probably be the answer, but that's assuming that it's perfectly symmetrical, which is not really what you should do, probably. So instead, what you can do is you can get this area and add it to the opposite of the negative value of this area. So the minus 1 multiplied by that area. So let's actually manually do that. So we say we first want to get minus 2 to 0, x3 minus 4x. So that's just this one in here. So that is equal to, we have these square brackets. We have 1 over 4 x to the power of 4 minus 1 over 2 x to the power of, oops, it's my mistake, minus 2 x to the power of 2, 0 minus 2 there. So if I substitute 0 in, that's going to be nothing. So I'm going to say 0, and then minus the second value we substitute in. So we have 1 over 4, then minus 2 to the power of 4, minus 2, then minus 2 to the power of 2. And that will give us minus 1 over 4 multiplied by 16 minus 2 multiplied by 4 is equal to 4 minus 8. We have a minus out the front there, is equal to 4. So that's our answer. So this area underneath the area underneath this side of the curve is 4. Now we could assume that this area is exactly the same, not just because we're assuming it's symmetrical, but because we already know that when we add this area and this area, it equals 0, which means this other area must be equal to minus 4. Instead of just like knowing that and putting that down in a test, a teacher might not even really realize that's how you solved it. So it's probably a little bit smarter just to actually solve it. So we're going to do another one of these square brackets over here. We're going to do 1 over 4. We're just going to copy our answers from over here. X to the power of 4 minus 2x, x squared. And this time we're going to go from 0 to 2 instead. So let's evaluate this. So our first value is 2. So we have 1 over 4, 2 to the power of 4, minus 2, 2 to the power of 2, and then minus 0. So we're just going to put 0 in those brackets because we know that everything gets multiplied by the 0. So it all equates to nothing. Now we have 1 over 4, 16 minus 8 is equal to 4. So our whole area is 4 plus 4. So a good way to sort of put these, they might have it over here. One way that you can actually one way you can actually write one of these, the formula to find the equation to find one of these relationships here, is you can say, okay, we need to split this up into multiple parts, right? So then what we're going to do, I'll give us some area by wiping everything. So then what we're going to do is we're going to oh, it starts at -2. We have -2 to 2, and then we have our equation, x to the power of 3 minus 4x, done. And then we're adding, this is 0, we're adding 0 to 2, x to the power of 3 minus 4x. And now some of these might end up being negative, which is not what we want. So since that's the case, we just like to put absolute brackets on the outside, so absolute value brackets. So that's saying these straight lines that go down, if you did this, it's 2 straight lines around 3, that's saying that is equal to 3. So that's what absolute value brackets sort of mean in the simplest sense. So that's what we do. So sometimes a line might have, it might dip below and above the curve a lot, and if that's the case, you would have multiple sets of these absolute value brackets for different domains that exist, and each domain changes when it dips below or above the brackets. So another route you can go is just any time that there is a negative area, you get each area and you see is the area negative? Okay, just make it positive. And that might be a little bit of a more consistent, easier way to go about it. Okay. So we want to find the shaded area of the shaded regions of these diagrams here. So let's do that. So I know I sort of know based on y is equal to x squared that this line hits 0, y is equal to 0, hits the x-axis at x is equal to 0. So I can just put a 0 in knowing that. So it's 0 to 3, because it gave us the 3 value there. It might sometimes give you something a bit more complicated. You know what, let's actually do a little bit more of a complicated version of this question. Let's say it asks us to find the area between the x-axis and the curve when y is equal to 0 and y is equal to, let's say, 9. Oh, that's too similar to our current question. Let's say 16. So if it told us this, find the area between the x-axis and the curve when y is equal to 16 and, for the range, I should say, for range y is equal to 16 and y is equal to 0. So that's saying, okay, we have our line here. At some point, y is equal to 16. At some point, y is equal to 0. Now, we're on the line. Now, we want to find the area on the line between these 2 points. So that means when we actually differentiate, we're doing things in terms of x, because what we're looking at when we derive and when we anti-differentiate, we're looking in terms of x because basically we're working with the x value. So in specialist math, you might see some more complicated things where you actually start differentiating with y, like if x is the subject, it gets more complicated. But for now, we're just thinking, okay, we're looking in terms of x. So we can't put 0 and 16 here and then put x squared. And the reason we can't do that is because if we do that, then we're actually finding when x is 0 and x is 16. That's the actual domain for which we're looking. Instead, we want to look for the range y is equal to 0 and y is equal to 16 to find the area under the curve between the points where y is equal to 0 and y is equal to 16. So then we just have to convert. We have to say, okay, we have to say what are the x values when y is equal to 0 and y is equal to 16. So we say 0 equals x squared. That means x is equal to 0 in that scenario. So one of our values is x is equal to 0. And now one of our other values is we have 16 as, we have 16 as y, so 16 is equal to x squared. That means x is equal to plus or minus the square root of 4. The square root of 16, which is equal to plus or minus 4. So there's two values. Now, I probably should have said more explicitly. We're looking for the range, the positive range. Sorry, I should have said it explicitly. We're looking for the area between the x-axis and the curve for the range y equals 0 and y equals 16 when x is above 0. My mistake. Because now there would be confusion as to whether we're looking at are we looking between 0 and minus 4, or are we looking between 0 and positive 4? But let's just look for 0 and positive 4. So we're going to say equals plus or minus 4, and we're going to look at the positive 4 value. So now we have what we're looking for this different question I've defined here. We have 0 to 4. That's our domain, because that domain defines the same range. When x is equal to 4, y is equal to 16. When x is equal to 0, y is equal to 0. So now we have x squared in this integral. So that would become 1 over 3 x cubed. And then we have this range here. So that would be 1 over 3, 4 cubed, subtract 0 in brackets there. So then the area beneath the curve is, they handpicked some things for it to be 3, so it's a little easier to work with. But we can find the area still. So we have 1 over 3 times 64. Yep, 1 over 3 times 64 minus 0 is equal to 64 over 3. So that's our area beneath the curve between the points where y is equal to 0 and y is equal to 16 on the positive side of the x-axis. So that's sort of a slightly more complicated question you'll get. There's just the extra step of finding what is the x value there, because they might give you a y value. They might give you some other more complicated things as well. Like they might say, oh, there's 2 points where where the line, what is the area on this line under this curve between the 2 points where it hits the x-axis. So if you had a line like this, let's say this is a parabola, it could tell you just find the area beneath there and the parabola is equal to this. And then you would have to manually find what are these points here. So that's just another level instead of it giving you these points. So let's do this question here. Find the shaded area underneath this line between 0 and 16, and the line is y is equal to the square root of x. So let's attempt to do this. So we have 0 and 16. Those are our x coordinates that we're looking between. Then we have the square root of x. This is the same as x to the power of 1 over 2. X to the power of 1 over 2. So if we're applying our formula, we would see, okay, that is equal to 1. And when you have 1 over 2 and stuff, it can be more easy to apply the formula that we have all the way like at the very, very, very start. This formula here, if you know this formula, it can be a bit easier to apply it. It can make things a bit easier when you can apply it to, like, you have a square root that you're looking at. So we have 1 over 2 plus 1 x 1 over 2 plus 1 there. And that's what we're worrying about here. So that's 1, and then there's 3 over 2 down here, plus x, 3 over 2. Getting there, 2 over 3, 3 over x. Okay. Okay. So now we can substitute our values in, as we usually do. We have 2 over 3 multiplied by 16 to the power of 3 over 2. Subtract, and then we can just say 0, because we know that 0 gets substituted into the only term, so the term is 0. Now, this doesn't look very fun to actually solve by hand, so I'm just going to plug it into a calculator. It'll make my job a bit easier, because a lot of these questions you will actually have calculator. Okay, so this comes up with 42.6667. So you're probably supposed to do this by hand because it doesn't look like a very pretty number on the calculator. Well, I guess what looks like a pretty number on the calculator is one that looks like you really can't do it by hand. But for now, we'll just leave it like this instead of bothering to do it by hand to expand any of that. It could even just be you leave it in this form as well, instead of bothering to do it for a lot of questions. You can get full marks for leaving it in that form. So now we're going to look at the area between two curves. So this can get pretty complicated, but at a basic level, what we're worried about is, okay, we want the area between this curve and this curve, which is just a straight line, it's not a curve. What we can do is we can get the area under this one here, and then we can get the area under all of this one here. So let's say we get the area under the linear line, and then we get the area under, let's say this is some sort of logarithmic line, some sort of exponential line. Then we can subtract the area underneath the linear line with the exponential line. So again, let's say it's even simpler if we have two linear lines. Let's say we want to get this area in here, and this line is B and this line is A. We can get the area of B minus the area of A, and that will give us the area under B that isn't under A, which is the area between B and A. So that's the basic idea. It can get a lot more complicated because it could be like, for example, you have this line here, and you want to get the area like between here and then between there as well, and then down there as well. And that could be a shaded region on the graph, and that would be really complicated to solve all of that, because these are actually 3 distinct areas you would have to get. 4 distinct areas you'd have to get, because you'd have to get, well, you'd have to get one area here, one area here, one area here. So there's a bunch of areas you'd have to find to be able to solve that. That is like a complex question that you could get on an exam to look at a sort of set of lines and find certain shaded regions between them. This is a pretty simple version of that. We just have 2 lines, there's one shaded region between them. So then we just have to find sort of where they collide. So that's our x values that we're going to look between, where they hit each other. And then when we do that, we're going to be able to get the area under the top curve minus the area under the bottom curve, and that's our answer. So let's say we wanted to do it here. We could try to do it we could try to do it here. So first we need to find we're going to assume that they collide at 1. We're going to assume that they intercept at 0, sorry, not 1. But they also intercept at 1. So we're just going to use the area between 0 and 1 here. And x squared seems to be the line on top. So we're going to do x squared to get this top area. So when we get x squared, we're going to get basically this whole area in here, right? But then if we can get the area down in here, we can subtract that from our x squared. So it looks something like this. That'll be our answer. This, if we can evaluate what this is equal to, we get our answer. So that's 1 over 3 x to the power of 3, 1, 0, subtracted by 1 over 4 x to the power of 4, 1 over 0. So not 1 over 0, 1, 0. Now we're going to evaluate each of these separately. So I'm going to put big brackets for the first one and then negative big brackets for the second one. You know what, we're going to need more space than this. Put it over here. Big brackets for the first one. Subtract big brackets for the second one because there is that negative value there. So we're going to substitute in 1. That's 1 over 3 times 1 to the power of 3. Then we don't need to bother about the 0 because the 0 will, you know, just cancel everything out. Subtract 1 over 4 times 1 to the power of 4 minus 0 there. So that's equal to 1 over 3 minus 1 over 4. And that's everything. So that's our answer. That's our area underneath that curve there. Which would be 3 over 12 minus 4 over 12. Other way around. 4 over 12 minus 3 over 12 is equal to 1 over 12. So that's our idea. Basically, we find the area underneath the top one, which would be all this area, and then we find the area underneath the bottom one, which would be a little less area, and then we subtract the bottom area with the area of the underneath the top one, and that gets us our overall area. So we can apply that a little bit more here. Now this one's a little bit more complicated because we only want to integrate this one in here between these two areas, whereas we want to integrate this one out here between all of this area. So let's do each of those steps quite separately. We go from -2 to 2. And we're going to put in 4 minus x squared. Now that will result in 4x minus 1 over 3 x to the power of 3. And then we have a 2 and a -2 that we have to substitute in. So that's equal to 4 times 2 minus 1 over 3 times 2 to the power of 3. Subtract 4 times -2 minus 1 over 3 times -2 to the power of 3. Equals 8 minus 1 over 3 times 8 minus -8 minus 1 over 3 times -8 equals 8 minus 8 over 3 plus 8. And that is, so this would become plus, so minus 8 over 3. So our first area is 16, and then we subtract 16 over 3. And we'll just leave it like that for now, as we get our second area. So now we want to get the area in here. This area is probably a lot smaller. So we'll do that all the way over here, where I'm starting now. 1, -1, and then 1, and then our line is 1, and then subtract x squared. So this becomes something like x minus 1 on 3 x cubed, 1 minus 1 there. So that's going to be our area. We have 1 minus 1 on 3 minus -1 minus 1 on 3 times minus 1. So that's 2 minus 2 on 3. So that's our second area. 2 minus 2 on 3 is our area in here, whereas 16 minus 16 on 3 is all of our area here. So we want to get this and subtract that. So we'll do that over here. Everything's a bit all over the place because we don't have too much space. Subtract 2 minus 2 on 3. So that becomes 18, 14 minus 14 on 3, which becomes 30 plus 12 over 3 minus 14 on 3, which is 28 on 3, I believe. Yep. So that's our area. We have 28 on 3, and it's good to do units, so you can just write units squared. That's something that I forget sometimes. It's good to put units in there because we are getting like a squared area. So it's definitely good to put units. Sometimes you'll get a problem-solving question which will actually rely on you putting, meters squared in there or something like that. Next we have this area here. It tells us the area between these two lines, which does make it easier. Again, often you would have to, do something like, let's say, simultaneous equations to actually try to find the point where these two lines intersect. That would be like a complicated scenario. So we want to find the area underneath all of this, and then the area underneath just this one, and subtract the latter from the former. So let's utilize this space in here again. The antidifferentiation of something that would be good to do here actually is to get everything in terms of, to get y to be the subject of everything, because since we're doing the differentiation in terms of x, that's what we need to do. If we were to try to differentiate y, we would have a problem because we would actually be finding the area here, like a horizontal area, which is sort of interesting, and you might deal with that in specialist math if any of you are a specialist math student. So let's first try to evaluate how do we get this in terms of x. So y is equal to the plus or minus the square root of x. Now, this isn't necessarily a function, which could make our job a little bit harder, but it doesn't, because in this range, we should be able to just consider one form of x. So here we know that x is always positive. We're always looking at we're always looking at a positive y value and a positive x value in this range. So we're just going to consider y is equal to the square root of x, so plus instead of negative. Because what this line will look like is it'll be symmetrical and it'll go down here as well. So if we were to look at plus and if we were to look at minus x, we would be getting this area in here. That's what we would be looking for if we wanted to look at minus x. We don't want to get that area. We want to look at the positive area that x is in up here. So we're just going to interpret plus or minus x, the square root of x, as just the square root of x. Now we have x is equal to 3y minus 2. That becomes 3y equals x plus 2, which is y equals x plus 2 all on 3. So let's get this top area first. We have the integral of this range here. We have 0. We're doing 1 to 4 this time actually. 1 to 4 square root of x. That's equal to. Now we might have back here. Do we have an example of us? I think we've already done integrating the square root of x, but we'll do it again. It should become 1 over 2 plus 1 x 1 over 2 plus 1 there. And that's what it looks like. And then we need to make sure we remember to put our boundaries in there. So we just apply, our typical method of finding the area by expanding these square brackets. Okay. So I'm not going to simplify this yet because this other line that we're looking at could maybe simplify it. Probably not though. It looks like a pretty simple linear equation, which means it probably won't simplify it any further. But I might just plug it all into the calculator at the end lazily as well, which I think can be productive, considering we only have about like 5 minutes left or something. So let's look at finding the differential of the bottom line so that we can subtract it from this value here. So it's a linear line. That makes our job pretty easy. We go 1 to 4, and we have x on 3 plus 2 on 3. So that becomes, well, that equals is a better way to put it. One on 6 x to the power of 2 plus 2 over 3 x. And we need to remember to put our 4 and our 1 here. Now we can open this up into being 1 over 6 times 4 squared plus 2 over 3 times 4 minus 1 over 6 minus 2 over 3. And that's our expanded form. Now we can throw everything together. So it becomes 2 over 3. So we're getting this top line area, 2 over 3 times 4 to the power of 3 over 2 minus 2 over 3. Then we're subtracting all of this other line that we've found, all of this other area. 1 over 6 times 16 plus 2 over 3 times 4 minus 1 over 6 minus 2 over 3. So some things cancel there. That's 2 over 3 times 4, 3 over 2. This cancels that one there. Minus 16 over 6 plus 8 over 3 minus 1 over 6. And we could keep working to simplify it, but I think, how many slides do we have left? We have a fair amount of actual content to get through, and I think everyone knows how to sort of go down and spend a lot of time simplifying all of those processes. So last, we're going to look at the trapezoidal rule. So basically what this is sometimes we might need to actually estimate what is the area underneath the curve instead of being able to actually find it. There's certain reasons for this. Sometimes we aren't able to find the antiderivative, so we will want to estimate what's underneath the curve. So the true area underneath the curve would, include all of this area underneath the blue stuff, but we can sort of estimate it with these trapezoids we've created in this diagram. So these trapezoids cover this area here. They don't cover all the blue area, or sometimes they go over the blue area. But that's the area we can use to estimate what is the area underneath the curve. So we've separated a line into segments, which we place trapezoids over, and then we get the area of the trapezoids, and that's how we find the area. So the area of one trapezium, that's probably in your formula sheet, will be h over 2, that's height. So in this scenario, we're actually considering height along this way. That's sort of the height of it. And a plus b, a is this, how high it is this way. So don't consider this height for now. Just consider this. Consider h width in the example of the trapezoidal rule. We have height goes along this way, and a is how high it is this way, and b is how high it is that way. So the area of one trapezium is sort of like this. A1, and H. Perhaps it would be better to do A1 and H. Then we have our second trapezium, which is connected. So, you know, if we have our trapezoidal rule representing a line, there'll be a set of sequential trapeziums that might represent, you know, a curve. So then A1, and then there'll be A prime, and then A double prime, then A triple prime. Those represent subsequent heights of the following lines. So our first trapezium has A and then A1 as its heights. Our second trapezium is A1 and A2 as its heights, because it shares one wall with our first trapezium. So there's A1 there, there's A1 there. Then our third trapezium would have A2 as its first wall, and then A3 as its next wall. And then you can continue that until AN plus B, plus the final height that we're worried about here. So that's basically what we're doing. We cut this line into evenly spaced segments, and they have to be evenly spaced because our spacing is H. And then we find the area of different trapezoids that we're able to cut out of our line. Now, if we sum all of that together, you'll find that you can put it in this form here. You can put it in the form of h over 2 outside of everything. You can go a plus b, so that's the height of the first wall plus the height of the last wall, plus 2, a1 plus a2, etc. So those are all of the inner walls. And that's because there's 2 instances of a1, there's 2 instances of a2, and there's 2 instances of every one of the inner wall. There's only 1 instance of each of the outer walls, and everything ends up being multiplied by h over 2. So that's what the trapezoidal rule becomes. I think it's in your formula sheet. If you're able to plug things into it properly, you'll succeed. You'll be able to estimate the area underneath the curve using that. So our last bit of work probably will have to be us. I'll quickly look at what we have ahead. Our last example will be us looking at actually applying this trapezoidal rule for this function here. So we want to estimate the area here. So we're not actually going to do the integral. We're going to find the area at different points. So with 5 function values, estimate. So that's saying with 5 different points along the line. We're going to just do 3. We're going to find 3 points along the line. So we're going to do 4 is probably the easiest actually. So 4 points along this line. Let's find the value here. We have 0, 1, 2, 3, 4. We'll keep 0, so it will actually be 5 values. That's my mistake. Now, we want to, so the line, let's say the line, it could look like anything. Let's say it looks like this. We want to chop it up into distinct parts, 5 distinct parts at 0, 1, 2, 3, 4. That means h is equal to 1 because the width of each one of these parts is 1. Now that means we actually have to find the height of each of these parts as well. So we have to find the height at 0, we'll call that A, then we have A1, then A2. So let's do that. So at 0, the height is 0 because we can see there's a leading x, which means if y is equal to x4 minus x and x is equal to 0, then y is equal to 0. when x is equal to 1, we want to find what y is equal to. So that's y is equal to 1 and then 4 minus 1. So that's y is equal to 3. Then when x is equal to 2, y is equal to 2, 4 minus 2. So that means y is equal to 4. When x is equal to 3, y is equal to 3, then 4 minus 3. So y is equal to 3. Lastly, when x is equal to 4, y is equal to 4, and then 4 minus 4. So y is equal in that scenario to 0. So what we have is we have this sort of symmetrical looking line, and we have 4 different heights that we have. We could try to sort of plot the heights of this line. So let's say we were looking here. At 0, we know the height is 0. At x equals 1, the height is 3. At x equals 2, the height is a bit higher at 4. Then the height goes back down, and then it goes back down to 0. And those are our parts that we're going to separate into different trapeziums. So now to do that, let's actually just throw everything into this formula. So we have all these 4 different heights. We can put them next to each other like this: 3, 4, 3. So that's x, that's y, 3, 4, 0. So our trapezium rule would say we have h over 2. H is 1, so it's 1 over 2 multiplied by 0 plus 0. So that's our a and that's our b, our first value and our last value, plus 2 times everything else. So that's 3 plus 4 plus 3. So that's 1 over 2 multiplied by 2 this time. So it just becomes 3 plus 4 plus 3. So our estimated area, not the true area, our estimated area is equal to 10. And that's our result. So basically, in simple, what we're doing is we're basically using a simple mathematical formula that I believe is on your formula sheet to estimate the area by separating a line into approximate trapeziums that cut up the line into these approximate parts. So we don't have the time for any more questions. If you could, you could take a screenshot or go back through the slides to look at this question, and this is the answer. That would be a good little practice for that rule that we're just looking at just then. So just to sort of summarize some things, you can use calculators to do a lot of these things. They're very useful, obviously, with usually the trapezoidal rule is a tech active question. You just have to very quickly plug everything into the calculator and hope you didn't make an error. So it's obviously good to check that sort of thing. But you can do definite integrals in your calculator, so it's very useful to learn to do that, because that will be on your exams, and you can also use it just while studying. It can make certain things a little bit quicker. Now, I would recommend for your assignment that you make sure you really look at your task sheet. I think some students have already done their assignment, but if you haven't yet, really do look at your task sheet. I've tutored some students, and I don't know if they've fully looked at their task sheet and really read it out themselves. And I think it is very useful, because even your teacher might miss something, and you might be missing the ways to get easy marks, and you might be spending a lot of your time on things that are less important. Allow the most time for the formulate section. That's very useful. I think it's the best marked section in general. Like, that it has the most marks in it, and it's easier to get the marks for the other sections than the formulate section. With exams, make sure you do practice exams, and make sure you use your perusal. Those are the 2 biggest things. Perusal, just so, like, I've never met a student that has comfortably finished every single grade 12 exam with so much extra time. It is always an experience of there's still, either they didn't even get to answer some questions because they had no idea, or they're still working a bit at the end, fixing up some questions, still checking, So it's best to do the questions that you know you can do first. Use perusal to mark the questions that you will be the likeliest able to do quite quickly. Okay, so I think that's everything. I hope I didn't go over too many things too quickly. I know I went over things a bit quickly at the end there, and I didn't fully bother to do all the working to get the final answer to some of the questions that I think are probably more likely actually calculated questions in the exam. But I hope you understood everything. Don't feel too stressed if you didn't. Remember, you have a whole year to study this stuff. We've covered like a few weeks of content in 2 hours. So really, like, just think of this as either a recap or an introduction to some concepts that you're actually going to get to know and get to learn in class. Okay. Um, Good luck.